Black holes are among the universe's most powerful and mysterious objects. Imagine a region where gravity is so intense that nothing, not even light, can escape. These cosmic monsters form when massive stars collapse, squeezing their matter into an unimaginably tiny point. Their gravity warps space and time, making them invisible to our eyes and telescopes. Instead, we detect black holes by observing their effects, how they pull on nearby stars and gas. Supermassive black holes anchor the centers of galaxies, including our Milky Way. They grow by consuming stars, gas, and merging with other black holes. For decades, black holes were just theoretical, mathematical predictions from Einstein's equations. We had indirect evidence, but no direct images. Capturing a picture of something so dark and distant seemed impossible. By linking radio telescopes across the globe, we created a virtual Earth-sized observatory. This global effort is driven by our desire to see the unseeable. The quest to image a black hole is a testament to human ingenuity. It's a story of turning the impossible into reality. On October 10, 2025, astronomers achieved the unimaginable, the first direct image of two supermassive black holes locked in orbit. This wasn't a simulation, it was a real radio image, revealing two cosmic giants circling each other. One black hole is a true titan, over 18 billion times the mass of our Sun. Its partner, though smaller, is still supermassive. These black holes are bound in a slow, majestic dance that's lasted millions of years. For the first time, we could visually separate two black holes in a binary system, moving from theory to direct observation. Each is surrounded by a halo of superheated, radio-emitting gas, swirling in space. They're so close that one day they'll merge, sending gravitational waves rippling through space-time. This discovery is like finding a living dinosaur, a direct window into a process we knew must happen, but had never seen. The image is more than a scientific milestone. It's a treasure trove of data about black hole growth, galaxy evolution, and gravity itself. It validates decades of theory and observation. When galaxies collide, their central black holes can find each other and begin this long, slow dance. This single image opens a new chapter in our exploration of the cosmos. To find these dancing black holes, astronomers looked 5 billion light-years away, into the heart of a quasar called OJ-287. Quasars are the brilliant, energetic centers of young galaxies, powered by supermassive black holes devouring matter. OJ-287 is one of the brightest and most studied quasars, a beacon from the distant universe. The larger black hole, with a mass of 18 billion suns, is surrounded by a massive accretion disk. The smaller black hole orbits on a tilted 12-year path, crashing through the disk twice each orbit. Each collision triggers a flare, an outburst of energy that makes the quasar shine even brighter. These predictable flares first tipped astronomers off to the presence of a binary system. Observing two separate black holes in such a distant, compact system is a monumental achievement. We're not just seeing two objects. We're witnessing a cosmic collision in slow motion, shaping both the black holes and their galaxy. The feat is like spotting a football on the moon from Earth, a testament to the power of modern astronomy. How did astronomers capture such a distant, tiny pair? They used very long baseline interferometry, or VLBI. By linking radio telescopes across the globe, they created a virtual telescope nearly the size of Earth. But to get even sharper detail, they added the Radio-Astron satellite, a radio telescope in orbit, reaching halfway to the moon. This Earth-space network achieved a resolution of just 12 micro-arcseconds, 100,000 times sharper than a typical optical telescope. It's like reading the date on a coin in New York from London. All telescopes had to observe OJ-287 simultaneously, recording faint radio waves. The data was combined and processed by supercomputers, taking years of meticulous work. This unprecedented resolution finally separated the two black holes in OJ-287. As lead researcher Maury Valtonen said, the space antenna turned a fuzzy blob into a clear portrait of two distinct objects. The groundbreaking image isn't colorful. It's a radio map showing two bright spots, the supermassive black holes. We're not seeing the black holes themselves, but the hot gas swirling around them. The brighter spot marks the larger black hole, the fainter, its smaller companion. A faint, curved jet emerges from the smaller black hole, a stream of high-energy particles blasted into space. Unlike most jets, This one is twisted into a corkscrew shape. The spiral is caused by the smaller black hole's rapid orbit, swinging its jet around. This wagging tail is the smoking gun, proving the smaller black hole is truly orbiting the larger one. If they were just neighbors, the jet would be straight. The curved jet confirms the powerful gravitational dance predicted by theory. This visual evidence matches decades of models and calculations. The image is a rich dataset, revealing the dynamics of this extraordinary system. It's a stunning breakthrough in our understanding of black holes. The story of OJ-287 is a cosmic detective tale decades in the making. In 1982, Finnish astronomer Imo Sillanpää noticed the quasar flared every 12 years. He proposed OJ-287 was a smaller black hole orbiting a larger one, causing predictable flares as it crashed through the accretion disk. This theory explained the observations perfectly, and astronomers used it to predict future flares, each one arriving right on schedule. The system became a unique laboratory for testing Einstein's general relativity, as the smaller black hole's orbit slowly precessed due to immense gravity. Accurate flare predictions matched Einstein's equations, providing strong, though indirect, evidence for the binary model. Still, some doubted, until the 2025 image provided direct visual proof. The image is the final piece of the puzzle, confirming Sillanpää's theory. OJ-287 is now a tangible, observed reality. This triumph concludes a 40-year scientific quest. It's a testament to patience, ingenuity, and the power of observation. This discovery is more than just two black holes. It's a new window into the universe's biggest mysteries. It shows how galaxies grow, merging and forming binary black holes like OJ-287. Studying this system reveals the final stages of galaxy mergers and tests the limits of physics. The gravitational forces here are extreme, letting us test Einstein's theory in ways never before possible. By tracking the black hole's orbits, we can measure energy loss from gravitational waves, ripples in spacetime. OJ-287 connects to gravitational wave astronomy, previewing signals from supermassive black hole mergers. Understanding this dance helps us predict and interpret future discoveries. The first image of two orbiting black holes is a landmark, confirming theories, testing physics, and revealing the violent processes that build galaxies. The universe is full of wonders waiting to be discovered. Each new breakthrough brings us closer to understanding our cosmic origins and fate.